the barnyard grass control, which is untreated, then the barnyard grass showing injury after treatment with glyphosate, then the barnyard grass showing injury after treatment with glyphosate plus adjuvant, the Palmer amaranth control, which is untreated, and the Palmer amaranth treated with glyphosate. Mobile net was chosen because it was necessary to select a mobile architecture that could run efficiently on mobile devices. Firstly, for its stepwise separable convolutions, which splits a standard convolution into 2 steps, making it more efficient. Firstly, a depthwise convolution, which applies a single filter to each input channel independently, primarily focusing on the spatial relationships within that channel, and a pointwise convolution, which is a 1-by-1 convolution that then combines these outputs to generate new feature representations. The advantages of this is that it dramatically reduces the number of parameters, lowers the memory usage, and decreases the computational cost. Next, for its transfer learning capability. MobileNet uses ImageNet with pre-trained weights, and these leverage previously learned visual features, which improves the convergence and generalization on limited datasets, such as our one. Lastly, MobileNet supports model scalability. It supports width multipliers, which reduce the computational cost by making the network thinner, and resolution multipliers, which further reduces cost by making the input image size smaller. This allows the developers to scale the model for stronger or weaker devices, making it perfect for rural agricultural environments. When compared to other convolutional neural networks, MobileNet is 8 to 9 times more effective, which makes it ideal for running inference on mobile devices. Under our materials and methods, a big part of our system's success was its curated annotated dataset, which consisted of 96 images in total, which 81 of these were training images and 15 of these were validation images, which allowed the unbiased model evaluation. These were captured under controlled experimental conditions, clearly representing injury symptoms such as necrosis, wilting, and tissue desiccation. Our training approach used was the transfer learning workflow, which used the pre-trained MobileNet backbone with the ImageNet weights. How this works is, firstly, the base model remained frozen to preserve feature extraction capability. Next, a global average pooling layer was added, which reduced dimensionality while still retaining important spatial information. And lastly, a dense softmax activation layer was added, which resulted in the 5-class probability distribution. This helped the model to reduce overfitting risk, which is when it learns the training data too closely but fails to generalize to new unseen data. Our training parameters included an epoch size of 50, which shows how thoroughly processed our dataset was. The batch size of 16 was small, however, it still proved to be effective. Our learning rate of 0.001 balanced the speed of convergence without the risk of overshooting the optimal solution. And the optimizer we used was Adam. When compared to other competitive optimizers such as STD, Adam converges better, handles sparse and noisy data well, requires less memory requirements, and less hyperparameter tuning. And our loss function was categorical cross-entropy, given that this was a classification model. Here we can see our results, and they show rapid convergence within the early epochs, showing how effective the learning was, and then there was a plateau across the rest of the epochs, showing the high accuracy of our model. There was close alignment between the training and validation accuracy, and as we can see that there was no divergence between these curves, indicating that there was no model overfitting. To further look at our results, we looked at prediction outputs of samples across all 5 classes. Here we can see our model was at least 98% effective all across the board. It could not only distinguish between the 2 wheat species, but also within them. For example, here in the middle, we have the barnyard grass treated with glyphosate, and it accurately predicted it 98% of the time, with only 2% misclassifying it as the barnyard grass control. There was also strong separation between the Palmer amaranth classes, despite its very small dataset. Our confusion matrix was used to evaluate the performance of our classification model. See, on our x-axis, we can see the predictions, and on the y-axis, we can see the actual classes. So for our results, All validation samples were correctly classified. There was clear distinction between the untreated and treated conditions, and the findings support our hypothesis. So here we can interpret that lightweight transfer learning models can achieve strong separation in agricultural applications. Transfer learning mitigates data size limitations in controlled experimental settings, and herbicide-induced physiological symptoms provide discriminative visual features for mobile AI classification. To highlight the novelty of our smart weed classifier, we compared it to another weed classification app called Seed. The smart weed classifier can not only distinguish between different weed species, but can also identify different herbicide combinations applied. It is also suitable for rural farming environments as it can be used completely offline without requiring any cloud or connectivity. Lastly, this model was exported to TensorFlow Lite for mobile integration. How this works is that the user captures an image of the weed, which is then processed by MIT App Inventor. Next, the image is classified using the Look extension, which doesn't require the internet, and the label to output mapping, which is already embedded in the system, allows users to see the results in real time in the app, as shown right here. The applications and impacts of this project for research includes very fast herbicide efficacy analysis. For extension, it allows farmers to correctly get the herbicide that they want. So it not only decreases the cost, but also increases the sustainability. For education, it can be used to support in-classroom or lab learning. And for precision agriculture, it has the potential to be integrated with spatial mapping or automated treatment logs. In conclusion, mobile deep learning is practical and effective for agricultural tasks. Lightweight neural networks can accurately classify weed species and herbicide injury conditions, and AI-based scouting tools can support research, education, and extension simultaneously. Although our early results are very promising, our future results include expanding the dataset, such as including new weed species, morning glory or water hemp, and different herbicide treatment conditions. This will improve the robustness of the model. Next, training on less controlled images, such as images with shadows and occlusions, variable lighting, or field level noise, because in rural environments, farmers can't always take high-resolution pictures. And lastly, we want to integrate a feedback loop where the user continuously submits improvements or images which further refine the model over time. Here are our references which supported our optimization frameworks. And I would like to acknowledge Dr. Michael Marshall and Dr. Matthew Katule for their contributions to this project. Thank you. I'd like to welcome any questions now.
Very well presented. Let's say a couple of farmers come to your place and ask how we can use this smart weed classifier. Then how would you explain to them?
How they can use it. So they can go into the field with their mobile device, and then all they do is take a picture of the weed, and then it will classify, like it will show the results in real time. Like as you can see through this image, like this is an actual screenshot from the app. So once they press this classify weed, it will show what kind of weed it is and what kind of herbicide treatment condition is applied to it as well.
This gives the